So, we have been discussing steady state analysis of mass transfer and biochemical reaction in immobilized enzyme reactors. The effect of mass transfer is demonstrated in the performance of immobilized enzyme reactor by virtue of the effect of linear feed velocity in the case of plug flow reactors, or effect of agitation speed in the case of a stir tank reactor, or the effect of particle dimensions or particle size on the performance of enzyme reactor. And these parameters influencing the rate of enzyme reaction or the performance of the immobilized enzyme reactor demonstrate the role of mass transfer in the performance of the enzymatic catalysis. Now, we have earlier seen the role of external film diffusion as a result of a thin film that is present on the surface of the catalyst particle in the case of a enzyme reactor, and we have considered the interaction of the film diffusion along with the biochemical reaction in the case of a non-porous particle, and a combined external film diffusion coefficient Kl along with the biochemical reaction constants was determined. The second case is about the pore diffusion, which in fact is much more pronounced in the case of enzyme catalyzed reactions, because in the case of porous matrices a very large surface area where the enzyme is present is through the pore surface in the catalyst particle. And so, obviously, the second case is if we consider a porous matrix in which the enzyme is immobilized throughout, will provide you the case of a pore diffusion regime. Now, in general, for an isothermal reaction, which usually most of the enzyme catalyzed reactions are, the effect of internal pore diffusion can be clubbed or can be expressed in a constant what we know as a parameter, what we know as effectiveness factor. The eta is called effectiveness factor. Now, eta essentially here is the ratio of actual reaction rate in the matrix in the presence of pore diffusion resistances. That means, as a result of the substrate concentration gradient that develops in the matrix phase to that of maximum reaction rate obtainable in the absence of any pore diffusional resistance. That means, if you consider particles, very fine particles in which the pore diffusional resistances may be negligible, or there are no substrate concentration gradient across the particle physical boundaries, and that means reaction is taking place in the particle at the same rate as in the bulk solution, and that ratio is called effectiveness factor practically. Now, of course, physically one can conceive the absence of pore diffusional resistances in the form of very small fine particles, to that of the particle which are of larger diameter and where the substrate concentration gradient becomes quite severe. Now, this effectiveness factor essentially has a number of characteristics. One is that in most cases the effectiveness factor will be less than or equal to 1, because the presence of pore diffusional limitations will always reduce the substrate concentration in the particle surface, and therefore, the substrate concentration at which the reaction will take place actually in the particle boundaries will be less than that in the bulk or at the surface, and therefore, the effectiveness factor will be less than or equal to 1. Of course, as I mentioned earlier, two specific cases demonstrate where the effectiveness factor can be more than 1. One is in the case of enzyme reactions which are controlled by substrate inhibition kinetics. That means, at the higher substrate concentration the reaction velocity is inhibited, therefore, as the substrate concentration gradient developed in the particle, the concentration drops and the reaction rate can be higher than at the surface, and therefore, the effectiveness factor can be more than 1. The second case is of the due to partitioning effect. If suppose the matrix is charged and the substrate is also charged, and if the two species have opposite charges, then the concentration of the substrate inside the reactor, inside the enzyme particle will be more than that in the bulk, and therefore, the enzyme reaction rate within the matrix may be more than what is obtained at the matrix surface, and therefore, the effectiveness factor can be more than 1 in the two cases that we have just elaborated. The second characteristic feature of the effectiveness factor is that it is inversely proportional to particle size. I mean, if you reduce the particle size, the effectiveness factor can approach to unity. That means, which essentially means that the whole of the matrix of the immobilized enzyme particle is able to get adequate substrate and carry out the biochemical reaction, and therefore, and in almost experimental conditions usually no pore diffusion resistance is obtained. That means, effectiveness factor is approaching 1 with particles of diameter less than 30 microns and average pore size greater than 2000 angstrom. That means, either of the pore diameter is large or the particle size is reduced, the effectiveness factor can be made to go towards 1. But of course, in these cases you face other operational problems, like if at the low particle size there is a risk of high pressure drop across the bed, and therefore, more power consumption for carrying out the operating the enzyme reactor. Also, the effectiveness problem can be more serious when the substrate of low diffusivity are to be processed. Now, if you take a substrate which has a lower diffusivity in the matrix, the problem is more serious, because the rate of diffusion is slower than the biochemical reaction rate. Therefore, the relative rate of diffusion and relative rate of biochemical reaction is another feature which controls the effectiveness factor. And of course, I think here also I must make it mention that the diffusional coefficient, the molecular diffusivity of a particular substrate in an empty matrix, and also in the case of a immobilized enzyme particle where the path of diffusion is quite haphazard, it makes quite a different diffusivity, and therefore, very often in the case of immobilized enzyme particle we call it effective diffusivity rather than diffusivity. You see, normally if we take an ordinary particle, a spherical particle where the pores are very uniform, say for example, you have a sphere where your pores are just identical. In the case of a, for example, control pore glass, then the path of diffusion is linear and of the same dimensions, whereas in the case of actual particles, what we encounter in the case of immobilized enzyme system, the path of diffusion is really not linear and uniform throughout the particle, and it can happen and that you have pores almost going in a random manner in the whole particle, and therefore, the diffusivity that we obtain from the theoretical consideration of a spherical particle may be in effect different than what is obtainable of a particle of that dimension, assuming a uniform cylindrical pore. We have also mentioned last time that if we want to analyze the simultaneous mass transfer and biochemical reaction in the matrix in a mobilized enzyme particle, it can be expressed assuming a cylindrical pore model. That means, we assume that the substrate diffuses into the particle in the form of a cylindrical pore. And I must mention that, as I mentioned just now, that in practice it may not be actually like a cylindrical pore, but just to simplify a geometric similarity and to analyze it, we are just assuming a cylindrical pore, and then instead of taking a diffusivity, molecular diffusivity, we consider a effective diffusivity, which takes care of the random nature of the pores. Now, the simultaneous mass transfer and biochemical reaction in the matrix can be analyzed in the form of a second order differential equation, dE d2s over dx square minus b prime equal to 1, where b prime is the apparent rate of reaction, that means under apparent kinetic parameters in the case of a mobilized enzyme, and dE is the effective diffusivity, and the substrate concentration profile here, let us say we consider this as a single pore, and obviously this pore refers to half the particle depth. There will be another pore on this side of the same dimension. So, whatever dimension of the particle we are considering, let us say if it is a palette of thickness 2L, we consider L as the thickness, because the substrate will be available accessible on both the sides. Similarly, if it is a sphere, then the radius is the major dimension, which is importance here in terms of x, and therefore, one need to consider only half the particle for analyzing or making such a analysis for getting a analytical solution for the substrate concentration profile. Now, the substrate concentration profile for such a situation, for such a second order differential equation, is usually obtained in terms of a Thiele modulus. Phi here is defined as a Thiele modulus in general, which is defined as a lump parameter like this, which is L into K true into S surface substrate concentration to the power m minus 1 upon dE and whole square root, and this is a general where K true is essentially the reaction kinetic constant in the absence of any pore diffusional effects, that means in the on the surface or in the bulk. Now, substrate SS is the substrate concentration of the surface, and m is the order of reaction, whatever is the order of reaction, and d is the effective diffusivity. Now, the solution of these differential equations is usually expressed in the form of Thiele modulus, and of course, a large number of workers have essentially given the solution of this expression both for zero order as well as first order reactions, for which the analytical solution can be easily obtained. Now, in the case of Michaelis-Menten kinetics, if we put the V dash term in the case of Michaelis-Menten kinetics, which is a non-linear expression, the analytical solutions are difficult, and usually you sort of approach numerical solutions, which have been also reported in literature. But very often for practical purposes, we try to look at our reaction conditions and assume and consider them that are they closer to zero order or first order, depending upon the percentage error that is involved in calculating the space time under the given set of conditions. Given set of conditions, as I say, are the inlet substrate concentration and outlet substrate concentration in the reactor, and within that regime, that means fractional conversion and initial substrate concentration. In that regime, if the reaction is more close to zero order, we very conveniently consider our system as zero order and make the design calculations, or if in case it is more closer, the percentage error is less. In the case of a first order kinetics, we go for a first order design calculations, but alternatively an exact solution using Michaelis-Menten kinetics also can be obtained numerically. Now, the effectiveness factor essentially for all those systems is a function of the Thiele modulus in all cases, whatever is the order of reaction, whether it is first order, zero order or Michaelis-Menten kinetics, the effectiveness factor is always a function of Thiele modulus, and this varies. The Thiele modulus, this function varies basically on the order of reaction as well as on the particle geometry. That means whether the particle is a sphere or a chip or a cylindrical fiber, cylindrical pallet or whatever is the shape, it varies on those factors, the relationship between the effectiveness factor and the Thiele modulus. Now, as I mentioned earlier, the Thiele modulus is a function of the true rate constant, the substrate concentration of the surface and effective diffusivity. And physically, if you look at, I think the Thiele modulus gives you an indication, although it is not an exact ratio, but it really gives you a ratio between the two reaction rate or reaction rate parameters rather to that of rate of diffusion. The numerator expresses a parameter resembling to the rate of reaction, and the denominator is the represents the rate of diffusion, and the Thiele modulus is essentially a expression of the ratio between the two things. So, therefore, basically if the Thiele modulus is high, means the reaction rate is faster. If the Thiele modulus is smaller, means the rate of diffusion is smaller. And of course, if you just simplify the Thiele modulus expression either for a 0 order or a first order reaction, it becomes still more simpler. For a 0 order system, it is L K true upon D into SS whole square root. That means the Thiele modulus is inversely proportional to the substrate concentration at the surface. On the other hand, for the first order reactions, the Thiele modulus is independent of substrate concentration, because 1 minus 1 is 0, and so it becomes independence of substrate concentration. Now, one can there are ample literature available from which one can write for pore diffusion controlled first order reactions in a packed bed reactor, assuming spherical particles in the packed bed reactor. The effectiveness factor is given as 1 upon phi within parenthesis 1 upon 10 3 phi minus 1 upon 3 phi, and that is the relationship between phi and effectiveness factor. And using this effectiveness factor, then you can write down in your reaction rate expression, and for first order kinetics one can write the reactor performance equation as epsilon tau is equal to minus Km upon K2 E naught, which is essentially the first order rate constant, into ln 1 minus x, and the expression for effectiveness factor that is given in the parenthesis. Essentially the expression in the parenthesis is same as, and you remember we have defined right in the beginning that the reactor performance can be simplified by taking a reaction rate expression which is multiplied by effectiveness factor. And so therefore, the tau, the space velocity or the space time can be given by the same design expression which was used for idealized enzyme reactors, excepting that an effectiveness factor for a case has been multiplied to the system. And of course, for the first order kinetics, this is the effectiveness factor as we discussed earlier. Now, this is in the case of spherical particles. Now, the same expression when you talk about packed bed of chips, that means very thin films of very fine thickness, let us say of the thickness L. In that case, the tau is given as K dash m ln 1 minus x upon K2 dash E naught, and the effectiveness factor essentially here is different as 10 hyperbolic phi upon phi, where the particle thickness is very small. So, these expressions have been obtained analytically in the case of different particle size, like in the case of thin films, and for spheres we have mentioned even for cylindrical pellets, discs. They have a number of such expressions are already available in the literature which can be used. Now, based on this, I think one of the major probably studies which were reported in 70s was particularly on the mass transfer in immobilized enzyme reactor by Robito and Kittrell. They made physical measurements experimentally of the Thiele modulus and also calculated the effectiveness factor based on these expressions, and they gave for both spheres as well as discs of different thicknesses, and confirmed the validity of the first order reaction rate expression applicable in many cases of packed bed reactors. And here the data points shown are essentially the experimental data with different particle sizes from say for example from 120 microns to 1000 microns. In fact, essentially they used control pour glass and immobilized it with glucose oxidase and measured the reactor performance with different particle sizes and made both experiment the value of effectiveness factor based on the experimental data, that means by taking as a ratio of the actual reaction rate for a particular particle diameter divided by the reaction rate at which particularly with a very small particle size, say 30 microns, and also calculated the same reactor performance using the analytically developed rate or the reactor design equations, and they found almost a very good fit both in the case of spheres as well as in the case of discs, and that is what confirmed the effectiveness factor. Y-axis is not, y-axis is effectiveness factor and Thiel modulus, and as a matter of fact the relationship between pore diffusion limitations and the Thiel and the Thiel modulus is expressed in terms of effectiveness factor, because if you know effectiveness factor you can have your reactor performance equation where you multiply your reactor rate expression. If it is a first order you multiply, let us say eta into K2E0 upon Km, the first order equivalent pseudo first order rate constant for an enzyme catalyzed reaction, or if it is 0 order K2E0 and you multiply by effectiveness factor if you are aware of that. Another thing which also has been checked experimentally, another factor which influences the reactor performance as a result of pore diffusion, the effect of increasing enzyme loading. Basically what you are doing when you increase enzyme loading, you are changing the Thiel modulus. The numerator in the Thiel modulus which gives you the reaction rate constant is increasing because the concentration is high. So, a K2E0 upon Km, if it is the first order rate constant in the case of a mobilized enzyme catalyzed reaction, then the value of E0 is increasing by enzyme loading, and therefore with enzyme loading, as you notice that as you increase the enzyme loading and in this direction and some arbitrary values of let us say 1, 10 and 100, you notice that effectiveness factor very sharply decreases. That means the enzyme becomes, or the reactor system, enzyme reactor system becomes more and more controlled by diffusional limitations, and when the enzyme loading is less, the diffusional limitations are less. I mean, as a matter of fact up to quite a large particle size it can be considered almost as a free of diffusional limitations.
So why is it so?
As I mentioned that you see the increasing enzyme loading influences the increase in phi, the Thiel modulus. The Thiel modulus on the numerator if you see is your K2, that is the true rate constant, which is essentially in the case of enzyme reactor is K2E0 upon Km in the case of first order, or in the case of 0 order it is K2E0. So, increasing enzyme loading means the loading is the concentration of enzyme is being increased, E0 is increasing, so phi is increasing, and Thiel modulus, increasing Thiel modulus gives you a lower effectiveness factor, and obviously which means that the rate of reaction is much faster than the rate of diffusion, and that is what the ratio is described by Thiel modulus, and therefore the effectiveness factor decreases. If you keep on increasing the loading, you will have a very significant effect upon your the final reactor performance, and ultimately it may happen that the rate of the loading may have no function, the whole reactor performance may be controlled by only rate of diffusion d. Here again another feature which in many cases have been numerical solutions have been found, where in the case of Michaelis-Menten kinetics, which indicates the effect of Thiel modulus on effectiveness factor as a function of beta, something like a dimensionless Michaelis-Menten constant, which is the ratio of K dash m upon S naught. Again it shows the effect of shift from your 0 order to first order. The shift is when K dash m is very small, when beta is small, the K dash m upon S naught is also small, and whereby you see the effect of beta on the effectiveness factor as a function of Thiele modulus, and in this case also as the Thiele modulus or the beta value increases, that means the reaction shifts from first order for 0 order to first order. The beta value increasing means from first order to, or from 0 order to first order, and in that case the effectiveness factor decreases, and the similar or the same effect on the Thiele modulus is obtained in either direction. So, essentially in the case of analysis of the internal pore diffusion in the case of a immobilized enzyme reactor, basically the analysis amounts to determination of a effectiveness factor for a particular system, and that is directly controlled by the value of diffusivity, effective diffusivity, the reaction rate constant, and on the size of particles what we are considering. Now, if you consider, say for example, a combined film and pore diffusional effects, and again for a simplistic case of a first order irreversible reaction, enzyme catalyzed reaction, we can club the two things, for example the film, external film diffusion and internal pore diffusion along with the biochemical reaction, and the flux of the substrate can be then written as, for example, J is equal to KL SB minus SS. You will recall that in the external film diffusion our flux of substrate along the particle surface is given by KL, which is external film diffusion coefficient into the substrate concentration gradient that is developed in the film, and that will be put equate to eta into Kf into SS. That means this is the factor, this is the rate of reaction or the flux through the pore diffusional limitation. In fact, the pore diffusional resistance is expressed by eta, Kf is the first order rate constant, or it can be also written as K2 dash E naught upon K dash m, and SS is the substrate concentration at the surface of the particle. Now, if you simplify this, you can write SB minus SS upon J equal to 1 upon KL, that is the inverse of the film diffusion coefficient, and also SS upon J is equal to 1 upon eta Kf, and therefore SB upon J is equal to 1 upon KL plus 1 upon eta Kf. So, basically if this is SB upon J is the main flux taking into account both external film diffusion as well as internal pore diffusion, and the first factor 1 upon KL is the resistance provided by external film diffusion, the second expression is a resistance term due to pore diffusion limitations, then the overall effect is a sum of these two resistances, and therefore one can obtain, now this essentially SB upon J will be the flux which will really be expressed in the case of a reactor performance which experiences both film diffusion as well as internal pore diffusion. So, therefore, if you, for example, if you carry out a immobilized enzyme reactor, a continuous immobilized enzyme reactor, and determine the reactor performance, and if you assume that you just carry out the reactor performance, steady state reactor performance at various fluid velocities, that is a linear flow velocities, what you are doing essentially you are varying the KL value. We know that the increasing the linear flow velocity will influence the KL value, and 1 upon KL will be 1 upon KL will be increased by the increasing flow velocity, the KL will decrease and the 1 upon KL will increase. And so, if you plot, let us say, flow rate inverse versus the overall rate constant 1 upon K dash. Now, this is we are defining this K dash as a reaction rate constant, apparent reaction rate constant, which takes into account biochemical reaction and also the external film diffusion as well as internal pore diffusion, and then you get almost a linear velocity with a intercept at 1 upon eta Kf, where Kf essentially is your pseudo first order rate constant. That means, if you carry out your reaction, basically to get such a performance, if you carry out the reaction at a low substrate concentration or even at a high substrate concentration, but the degree of conversion, fractional conversion is very high, where the reactor performance will be closer to a first order kinetics. You see, if you consider the reactor performance in terms of 0 order or first order kinetics, if you take any substrate concentration at the feed and carry out the substrate conversion to a very high level, and you will have the reactor overall reactor performance which is much closer to a first order kinetics. If the conversion level is not very high, then the reactor performance will be controlled by 0 order kinetics. If the outlet substrate concentration is also very high compared to the inlet substrate concentration, the reaction can be considered or at least approximated to be equal to 0 order kinetics. But if the conversion is very high, whereas so that the outlet substrate concentration is very low, then you can always approximate to be a first order reaction. And if you carry out that and carry out the steady state reactor performance as a function of flow rate and determine the overall reaction rate constant based on the reactor performance data, and then you can determine by the intercept 1 upon eta Kf. Kf is assumed and is known to you depending on the kinetic parameters of the immobilized enzyme. So, the value of effectiveness factor can be theoretically calculated, and which gives you, and also the K dash is essentially the overall reaction rate constant, which takes into account the biochemical reaction and the combined film and pore diffusional effects, and which can be also used essentially, the K dash can be used as a first order rate constant for design of the reaction, the immobilized enzyme continuous reactor. Finally, I would like you to leave with a small exercise. That means, if we consider that the analytical solution of a internal pore diffusion and biochemical reaction can be determined by a second order differential equation, and if let us assume that we have given some solution for the first order reactions, if we assume that the reaction is towards 0 order kinetics, that means the initial substrate concentration used is high and fractional conversion is also not very high, where let us say if you start the feed inlet concentration say at 100 km value, 100 times the km value, and the final substrate concentration from the effluent is let us say 50 km, the whole reactor will operate almost closer to a 0 order enzyme. And if that expression can be given by dE d2s over dx square minus k2 dash E naught is equal to 0, and if you consider that we are talking of let us say a disc, a thick a sort of a cylindrical disc with a thickness of 2L, now we would like to I would like you to develop solve the equation to get the substrate concentration profile as a function of distance from the center. Let us say if you give this is the distance x on either side, that means the thickness, the distance of the surface from the center is x, and on either side, and the substrate concentration profile in such a sort of thick membrane it need to be evaluated based on the second order differential equation. Obviously, the boundary conditions in such a case will be x is equal to L, S is equal to SS. Now, you can consider the substrate concentration as SS if you just leave out the external film diffusion, and it is SS, and on the other hand you at x is equal to 0, that means at the center of the particle the ds over dx is also equal to 0. under these two boundary conditions, if you simplify and get a expression for, let us say, S upon SS, and rearrange that in the form of Thiel modulus. That means essentially for a 0 order, phi 0 is equal to L K K2 dash E naught upon dE into SS to the power half, isn't it? Now, Thiel modulus will be this one, and so rearrange this expression in the form of phi and get the reactor performance, or you can also find it out that at what thickness from x from the center, at what value of x, let us say x is equal to some critical value of L, when the substrate concentration becomes approaches to 0. That means that fraction of the enzyme will be ineffective, and the ratio of that the two, that is L over LC or other L over LC, will give you effectiveness factor. So, I would like you to do this exercise and solve this differential equation under these boundary conditions and arrive at two things. One is the substrate concentration profile within the immobilized enzyme particle, and in terms of surface substrate concentration, and second thing is this length from the center, the value of LC at which the substrate concentration tends to be 0. If we assume that, then obviously your the boundary conditions will change, the boundary conditions will change. Is that all right? So, I think we